So thank you very much. I'll introduce myself. My name is Shlomi Reuveni. I'm from the School of Chemistry at Tel Aviv University. And let me start by thanking the organizers, Arnab and Pinaki, for inviting me. I would also like to apologize for not being able to be there with you in person. Unfortunately, I'm dealing with some medical issues, and these prevented my arrival to India this time, but hopefully I'll be able to come next time. My talk today is going to be dedicated to cues with service resetting, and this is a conference on frontiers in non-equilibrium physics, and one research topic that was at the frontier of non-equilibrium statistical physics in the last decade was stochastic resetting in applications. And this is really a talk about the applications of stochastic resetting to a real world problem. And what I'm going to do in the first part of my talk is introduce you to this problem. So you're all familiar with queues. You all had the pleasure to stand in line, either in the bank or waiting for food in the cantina. We have queues in the supermarket and so on and so forth. So queues are prevalent, and actually they also appear outside our daily lives in computer server systems. There are jobs waiting in line to be executed one by one by the CPU. In our bodies, in our cells, we have queues of molecules queuing up to be converted or degraded by enzymes into other molecules, and so on and so forth. From the micro scale to the macro scale, we have queue structures forming spontaneously. And what I'll do in the first part of my talk is introduce you to a certain type of problem that arises in such queuing systems. And this is the problem of service time fluctuations. I'll basically turn your attention to the fact that service time fluctuations are a major source of backlogs and delays in queues. And they could actually cause situations where you have a lot of jobs waiting in line, so blow up of the queue size. Then I'll talk about, so because this is an important problem that people try to solve in all sorts of different means, I'll talk about the state-of-the-art solutions to this problem, and I'll really introduce you to this, nothing more than that. And then I'll turn your attention to the fact that these state-of-the-art solutions don't always work. There are situations where they fail completely. And then I'll show you that exactly in these situations where state-of-the-art solutions fail, this is when you would like to use stochastic resetting, service resetting, in order to provide a different solution to the same problem. So this is a bird's eye view of the talk. So basically, the solution is that stochastic resetting is going to take a long queue and make it a much shorter queue, and I'll explain why as we go along. And so if you're not familiar with stochastic resetting, that's okay, because I'm going to introduce you to stochastic resetting in the context of queuing systems. And if you are, then you'll see yet another application of this very nice idea in a completely different system. Before I start, I want to give credit where credit is due. So who really did the work? Two people. Ofer Klauber was a PhD student in the group, and you already had a chance to hear from him. He talked about the Sokoban random walk and the breakdown of the percolation transition. And Arnab Pal, which you all know, of course, while he was a postdoc in the group. And paper is titled "Mitigating Long Queues and Waiting Times with Service Resetting." It was published in PNAS Nexus, and this is the reference. Okay, so now I think we're all set, and we can start, and I can introduce you to the problem that we're trying to solve. And in order to do that, we'll have to think a little bit about what determines the mean length of a queue that stretches in front of a service station. So basically, imagine this situation where you have a receptionist and people come into this queue, join this queue every once in a while, and the receptionist is dealing with them, and once he's done, they leave. So you have stochastic entry and also stochastic departures. this queue, and the queue size fluctuates. But let's just focus on the mean of this queue size and try to understand what controls it at the steady state. So if you think about it for a minute, you'll come to the conclusion that the two things must come into the equation. One of them is the arrival rate, basically the rate at which people join the queue. The higher this rate is, the longer the queue that you expect to see on average. And then another thing is the rate of service. The higher this rate is, the shorter the queue you expect to see on average. And of course, there's going to be a competition between these two factors to determine the mean queue size. And so this is embodied by what people now refer to as the Pollaczek-Khinchine formula, which is named after these two gentlemen that you may know from their other contributions, Felix Pollaczek and Alexander Khinchine. And so here I'm denoting by n the number of people standing in line, or the number of jobs. These don't have to be people. It could be jobs in a computer server, or molecules in an enzymatic queue, what have you. And this is the average of this quantity. And the formula that gives me this average is written here, and it's expressed basically in terms of the mean arrival rate to the queue lambda, and the mean service rate, mu, but not independently. You actually need to look at the ratio. The ratio is what matters, and this ratio is known in queue theory as the utilization, and it's denoted here by rho. And as long as the service rate is higher than the arrival rate, basically as long as the server is faster than jobs coming in, then the server can cope with the amount of work coming in. Then you'll get a steady state, and this steady state will have a finite mean, and this mean is given by this formula, rho over 1 minus rho. And you see that as the arrival rate approaches the service rate from below, then this term here basically explodes, and this embodies the fact that basically the server is swamped, and you get longer and longer and longer queues. Okay. So if this was the end, I would not be giving this talk today. It turns out that there is another term. There's another term to this equation, and this term has two parts to it. One, this part right here, rho squared over 1 minus rho, is similar to the first term, but then it is multiplied by something else. And this something turns out to be sensitive to service time fluctuations. And so if S is the stochastic service time of a single job, S average I denote here, and 1 over S average is just the service rate. But I can also look at fluctuations around the mean service time. And I can look at a dimensionless measure for these fluctuations known as the coefficient of variation. Here it's the coefficient of variation squared. The variance in the service time over the mean service time squared. And it turns out that this CV squared, this dimensionless measure of fluctuations, feed in to this formula. And what you can see, two things you should note. One thing is that this thing is a monotonically increasing function of the CV, of the relative fluctuations. The larger the fluctuations are, the larger this mean is. And another thing that you should observe is that there is a transition point which occurs exactly at CV equals 1. So it's monotonically increasing, but the contribution of this term can be either negative. If there are small fluctuations, it's actually negative, smaller than 1, if CV is smaller than 1. If CV is larger than 1, this contribution is positive, okay? And in particular, in situations where CV is large, there are large fluctuations in service time compared to the mean, then the contribution of this term dominates. And this is a real problem that people encountered when dealing with the queuing systems. And so what I'm basically telling you is that next time when you go to the supermarket and you see people standing in line and they have different numbers of items in their grocery bags, then this will of course lead to service time variability at the cashier, and service time variability by the PK formula will translate into longer queues. longer queues on the average, okay? So fluctuations in one quantity, the service time, somehow feed in to determine the mean of another quantity, the queue length. And this is intriguing because it leads to the breakdown of mean level analysis. There is no way to reason just by means and get the right answer. It's not enough to know the mean rate of arrival and the mean rate of service. You also need to know fluctuations in order for what? In order for you to characterize the mean, just the mean, not the distribution, the mean of the number of jobs that stand in line. And of course, every time we get something like this, in physics, in chemistry, in engineering, in the sciences, we celebrate because it means that there's something deep hiding underneath the hood. And there are many examples to situations where means of one quantity are somehow sensitive to fluctuations in another. And one which is very close to our heart, and this is just a reminder for the talk of my PhD student, Yuval Sher. He showed you in the first day of the conference that if you have a gated reaction, a situation where a molecule switches between a reactive and a non-reactive state, and you're asking how much time will it take this molecule to react with another molecule that maybe sits here, it's not enough to know averages, the average time it takes this molecule to get to the reaction center, the average probability to react, and maybe the average time it takes this molecule to loop and come back again, provided that it did not react upon the first collision. It's not enough to know these averages. You actually need to know the full distribution of the return time in order to know what? The mean, just the mean of the time it takes this reaction to complete. And so this is yet another example, and we're very excited by situations like this. So now coming back to queues, why is it that fluctuations in the service time actually affect the mean of the queue length? This is not clear. So at face value, imagine what is going on. So I'm doing my shoppings in the supermarket, and then I join this queue, and I see that there are a couple of people in front of me, and so I ask myself, okay, how much time will it take me now? How much time on average will I need to wait before the cashier starts to take care of me? And so I denoted this time here by W average. And so what do I do in order to get it? I look, there's 1, 2, 3, 4, 5, 6 people in front of me, basically 5 standing in line, and then another one in service. And each will take on average S average. S is the service time. S average time units to serve, and so I will need to wait 6 times S average before I'm being dealt with. So there is no fluctuations in this formula, and yet there were fluctuations in the PK formula, and so you maybe are puzzled by what is it that makes fluctuation appear. And it turns out that I did this calculation, but it's actually wrong. There's a wrong step here, and what I did wrong was to neglect the fact that this person here that stands and is already in service, the service time of this person when I join the queue is not S average. It's not like a new person that is starting service. Rather, this person is already in the process of being served. And so I need to look at the mean time of the remaining, or basically the remaining service time, and look at the average of that. And so you could say, okay, but this is surely less than the time it takes you to serve a new customer. But then you'll be wrong. And it turns out that you'll be wrong because of something called the inspection paradox. So the inspection paradox actually tells us that we're biased when we're visiting something at a random time because we're sampling time points with uniform probability. We're biased to sample longer intervals. And what this basically means is that we're more likely to fall on these customers that take longer to be served. And this introduces a sensitivity to fluctuations here. It turns out that mean remaining time of service of a customer that is already in progress is not S average. Rather, it's S average times CV squared plus 1 over 2. And if you look at this factor right here, you'll see that when CV is larger than 1, this is actually larger than S average. This will be larger than 1. CV is larger than 1. This factor is larger than 1. And then the entire thing is larger than S average. And you'll actually need to wait more than you expected. So this is the gist of why fluctuations are a nuisance in queuing, and they result really in major backlogs and delays. So now an interim summary. What did I tell you so far? I told you that if you compare two queues that are almost the same arrival rate, and they have servers with the same mean service time, but the blue server has smaller fluctuations around the mean than the red, then you're going to see larger queues forming behind the red server, larger queues on the average. And so the take home is that fluctuations in service times are a major source of backlogs and delays, and people know this for a very long time, and they thought about various types of solutions to this problem. One class of solutions is known as scheduling policies. And really, people write books on scheduling policies, so I'm just going to give you the gist. And this is the idea. So you have basically jobs coming into your queue, and you serve them. But then every once in a while, you get a very big job, and you know that if you're going to start serving this big job, you're going to have a long queue forming behind it, and this is bad, so you don't want that. So what do you do instead? You serve the shortest job first. So you pay in fairness. You don't serve according to the order of arrival. Rather, you schedule differently. You serve the shortest job first. Hence, and the effect of that is basically to create shorter queues. And there are variants on this scheduling policies, more sophisticated in other situations, and they work very well until they fail. And there are situations where these scheduling policies fail. And one class of situations like that you can immediately observe is a situation where, okay, if I want to do scheduling, if I want to serve the shortest job first, I need to know that this is the shortest job, and then the next one is maybe the one that will take me slightly more time to serve, and so on and so forth. In other words, I need to know when a job is coming in, I need to know how much time will it take me to serve this job. However, this is not always possible. So in the supermarket, you can maybe look at the grocery cart, and just by sizing that up, you could know roughly how much it will take you to serve. But there are situations where you don't know a priori how much time it will take you to serve a customer or complete service for a job. So imagine, again, a computer server, okay? And I'm sending this computer server a problem that I want to solve, but I'm using a non-deterministic, a stochastic algorithm in order to solve this problem. So maybe, and this is a canonical example, okay, I'm trying to find the global minima of some energy landscape. So perhaps I did some stochastic search, and I spent some time here, and then I fell into this minima, this global minima, and I found it, okay? But before, I spent some time in this local minima, but there's another scenario where I go directly, okay? And you can imagine that the discrepancy in the time it took me to find the global minima here versus here, this was slower, this was faster. This discrepancy can become huge if the energy landscape is very complicated. So when I'm trying to solve mathematical problems in some sort of a probabilistic way or stochastic way, I don't know, even though I have the same instance of the problem, I don't know a priori how much time will it take my algorithm to come back and return a solution. Okay, so this is one class where I cannot use scheduling policies because I don't know what is the shortest job, okay, beforehand. Another situation is the situation of catalysis, enzymatic catalysis. You have enzymes catalyzing many different reactions, but let's think about a simple case where we have one enzyme catalyzing a specific reaction. So one enzyme, one substrate, and the substrate molecules of this enzyme that are being converted to a different type of molecule, they're all the same. They're chemically the same, and yet, because of thermal fluctuations, the conversion time of a substrate molecule to a product molecule will be different at each cycle. And so here too, this is a situation where the fluctuations in service time, the server here is the enzyme, they are intrinsic to the server, and you cannot know how much time it will take you to finish this conversion. You cannot know a priori, and this is again despite the fact that the job is identical. You're working on the same molecule chemically. You have many of them. You work on these molecules, but you have large fluctuations in conversion times. So again, I'm repeating in situations where the fluctuations in the service time are intrinsic to the server, we cannot apply scheduling policies, and then the question is what do we do instead? So there has been a recent advancement in statistical physics out of equilibrium in the last decade, and this is stochastic resetting, and we've recently celebrated the 10-year anniversary of a paper that really started the boom of research in this field, diffusion with stochastic resetting by Martin Evans and Satya Majumdar. And here you see the first experimental realization of this process, which was done in the lab of Yael Roichman. And you see a particle diffusing, and from time to time, a computer algorithm comes and with optical tweezers drags this particle back to the origin. So this is stochastic resetting, just a visualization of that. And there are many different, it turns out, applications to stochastic resetting, and we thought, why not try and apply stochastic resetting in the context of queuing? And so this is the basic idea. Imagine really that I have a server, and all the fluctuations in service time are coming from the server itself. So what happens when a job comes in? I'm basically assigning some random service time to this job, but I don't know what the service time is. I need to wait it out, and then when it happens, and the job clears from the system. So one thing that could happen is that I will just by chance get something from the tail of the distribution, the right tail of the distribution. And then, it will take a long time for me to serve this job, and other jobs will come in. And if I'm not going to do anything else, then this is the situation. However, what I can try and do is maybe say the following: if service does not complete up until some time, and this time could be up to me to decide. It could be drawn from another distribution. It could be stochastic or deterministic. Then what am I going to do? I'm going to start service all over again. So if I don't find the global minima of my energy landscape fast enough, I'm going to forget what I did and just start all over again, because I know it's the same instance of the problem. Let me start fresh. And now maybe, just maybe, I'm going to draw a short completion time, and I'll get the answer quickly. So this works nice in a cartoon, but of course I picked the example, and the question is, does it really work? So can we show something? Can we do some analysis to show that it works in general? And so how every time you come to a triangle, it doesn't matter how it looks, and you sum its angles, you always get 180. In very much the same way, it's possible to show something quite general on stochastic processes under resetting. So if you have a stochastic process that takes you from start to finish, any stochastic process, any start to finish that you can imagine, just anything that has a starting point, a finish point, and some random time t between them. And moreover, if this random time t has large fluctuations compared to the mean, so if the standard deviation of this random time t is larger than the mean of this random time, such that the CV of this random time is larger than 1, then I can tell you, and this is a mathematical theorem, that restart can be used to help you finish faster. And so any stochastic process or task with a CV that is larger than 1 can be accelerated with resetting. And why is this important in the context of queuing? Because in the context of queuing, service processes with CV larger than 1 are these service processes which cause major backlogs and delays. And so exactly when fluctuations are bad and deleterious in queues, this is actually turns out to be exactly the point where resetting can be used in order to help us expedite completion and service. And you might be wondering, is this a coincidence? So how come queues and resetting has this very strong connection with this quantity of the CV, the coefficient of variation, the ratio between the standard deviation and the mean? And it turns out not to be a coincidence. It turns out also to be a direct result of the inspection paradox that I mentioned. And so we've written a viewpoint on this, and this is really directed at students and newcomers to the field, because you can show with really elementary mathematical tools that the sole reason that stochastic resetting actually works to expedite processes is because of the inspection paradox, and this is why you get this CV dependence. So this is work that we did with Arnav Pal and Sarah Kostinsky, who was also a postdoc at the group at the time, and I invite you all to read it. So there's no coincidence. Resetting can be used exactly when fluctuations are large, and so now the idea is let's fight fluctuations with resetting, because this is the ideal tool to fight fluctuations with. And so now I'm showing you what can be done with this. Again, very general. We take a queue, and then what do we know? We know that the mean number of jobs at steady state is going to be given by the Pollaczek-Khinchine formula. Now, if the fluctuations are larger than 1, then this term here has a large contribution, and we somehow want to get rid of this contribution. So what are we going to do? We're going to add resetting to the service process. So I'm going to reset, say with a constant rate. If my jobs do not complete, I'm going to reset at a constant rate, basically have some rate R, and every time unit, every small time interval delta t, I'm going to have a probability R times delta t to reset the service process and start fresh. In order to analyze what is going on in the case where we have resetting, we need to understand, because these fit into the PK formula, what is the mean and the variance of the service time with resetting. And so what we can tell you in quite a general way is that if you start with a CV that is larger than 1, you're guaranteed to have a resetting rate that improves or basically reduces the service time. Or increases the service rate. And moreover, you can play around with this resetting rate so that you'll get the optimal resetting rate, so that you'll get the smallest smallest service time that you could possibly get. And I denote this optimal resetting rate by R star. And so if you start with a CV larger than 1, you're guaranteed to have a resetting rate that reduces your mean service time. What do we know about what happens to the fluctuations at this optimum? We actually know also something that is very general. It holds true for any first passage time process, also for a service process, which can be viewed as a first passage time process. We know that at optimality, the CV is going to be exactly 1. And so what this results is that the result of this, or the conclusion, is that we're actually killing, when we're adding resetting, we're killing this term because CV at optimal resetting is going to be exactly 1. And what about the second term? Well, here we have the ratio of lambda and mu, the service rate, but the service time now at optimal resetting is smaller than the service time without resetting. And so this row is also going to be smaller. So we're serving faster. We're going to have less jobs in the queue. And so we are getting rid of the positive contribution of this term because we started with a CV larger than 1. And we're reducing the number that sits here. And so the net result of this double advantage is that the number of jobs in the queue at optimal resetting is going to be smaller than what it was without resetting. And this is really general. It works for any service time distribution that has a CV that is larger than 1, which again is the problematic case that we're trying to solve. Can we do better than that? Turns out that we can. We can also optimize not only over the resetting rate, but we can optimize over all the possible set of resetting strategies. And we actually know that the best resetting strategy that we can use is sharp resetting. So instead of drawing the resetting time stochastically, basically picking a constant resetting rate is taking an exponentially distributed resetting time. Instead of doing that, we can decide that we're going to wait some time and then reset basically after this time has come. So basically I have a timer, a sharp timer, and I'm resetting at this time. And now I can optimize this timer. And it turns out that this sharp resetting strategy will beat any other resetting strategy that you can imagine. And in particular, it will beat the constant rate resetting. And so what you're going to get by applying sharp resetting is a mean service time that is even smaller than the mean service time that you have for constant rate resetting. And what about the CV? Because maybe you're reducing the mean, but you're paying somehow with fluctuations. Actually, no, this is not the case. You're guaranteed that you will also lower the fluctuations around the service time mean. And so now what we have is a series of inequalities, and basically what sits at the rightmost end of this inequality is the mean number of jobs under an optimal sharp resetting policy, and this is smaller than the mean number of jobs under an optimal constant rate resetting policy, which in turn is smaller than the mean number of jobs that we started with. Okay, so let me give you just one example out of the many that we did in the paper. And so here I'm basically taking a queue and I'm plotting the mean number of jobs in this queue as a function of the squared coefficient of variation. And the service time distribution here was taken to be log normal. It has 2 parameters. So what you can do is set the mean to be 1, fixed, and then play around with the coefficient of variation by playing around with the other parameter. And we've also picked some arrival rate that is comparable to the service rate. Okay, so what do you see? So without resetting, you have the PK formula, and the PK formula just tells you that the mean number of jobs is a monotonically, actually linear function of the squared coefficient of variation. So the more fluctuations, the more number of jobs that you're going to have in your queue. However, this is now what I'm plotting here and here. What happens when you apply optimal Poissonian, basically constant rate or sharp resetting? Then for Poissonian resetting, you see that exactly when the coefficient of variation is 1, you start deviating from the PK formula. And in fact, this curve goes down, and it eventually, when fluctuations are high enough, it crosses it and even goes below the mean number of jobs that you have in the absence, complete absence of fluctuations in the service time. And so what this is doing is turning a drawback, a huge drawback that we have in queues, and turning it into an advantage. We're actually using these fluctuations that would bring us to, I don't know, some very high mean job number here. We're using them in order to reduce the number of jobs even below what it was in the complete absence of fluctuations. And you can see that the sharp resetting policy is doing the same thing, but even better. Okay, so this is now the time to conclude. What are the take-home messages from this talk? Fluctuations are bad for queues in waiting times, and they're a major source of backlogs and delays. In order to solve this problem, people came up with scheduling policies, and these are very effective. They're the go-to mitigation tool. But in many situations, particularly in the situation where fluctuations in service times are intrinsic to the server, you cannot apply scheduling policies because you don't know how to schedule, because you don't know the service time a priori. And then what you can do is apply resetting. Resetting can be used to fight these fluctuations, and I showed you that it's actually turning this problem into an advantage. And of course, this was just the gist of the matter. In the paper, we did many more examples. We also went on and elaborated the discussion beyond the mean and onto the full distribution of full steady state distribution of the number of jobs in the queue with resetting. And another interesting thing that we were able to show is that there are also situations that you can imagine where you start with a queue that has some sort of a service time distribution with an infinite, basically a diverging standard deviation. And in this case, the PK formula tells you that there isn't going to be a steady state. The mean queue size is just going to explode. Or even a diverging mean. And in this case, again, the service is very slow. You cannot cope with the jobs coming in. However, what we showed in the paper is that when you apply resetting, you regularize the problem and you turn basically a defective queue into a working queue, one in which you have finite mean number of jobs in the queue. So additional details, derivations, explanations appear in the paper. This is the reference, and with this, I would thank you all for staying. I know that I'm the last talk, and I'm keeping you from lunch. I would like to thank again the people behind this research, Ofek Lauber and Arnab, and other members of the group. And if there are any questions, I would happily take them. Okay, thank you very much.
I hope you heard the applause a little bit at least. Okay, we have time for questions.
Hi, thanks for nice time. I have three quick questions. One, I didn't exactly follow. How do you actually reset a queue? What is the actual operational way to reset a queue? And second question is, why does fluctuations in the arrival rate of the persons in the queue does not figure out in the equation, and only the service time fluctuations figure in the equation? And the third question is, why no cortices, etc., will appear in these formulas? Higher order moments.
Yeah, so great questions, really great questions, and maybe I'll answer them from the starting from the last. Okay, you're asking how come this formula is not sensitive to higher moments of the distribution. And it turns out that if you are only interested in the mean, then what matters are the first two moments. Okay. Now, if you want the entire distribution, you will need to know the full distribution of the service time, and there is a distributional version of the Pollaczek-Khinchine formula. Now, you asked something else, which is also a very great question, and you actually found a place where I was cheating a little bit, where I wasn't cheating, but I was maybe zooming in on a particular a case of interest. Throughout this talk, I was assuming that you have an arrival rate lambda, which is constant. Basically, arrivals follow a Poisson process, but the service time distribution can be general. And I focused on the properties of the service time distribution, mainly the first two moments come into play. However, if the arrival rate distribution, if the arrival process is not a Poisson process, you have maybe not exponential times between arrivals of jobs, but a general distribution, some renewal process that governs the arrival process, then you will see a contribution coming from fluctuations in the arrival time. However, it's very hard for you to control as a server these fluctuations, because they're intrinsic. They're basically coming from outside the system. So there is this contribution, and it is important. Today, I did not discuss it because this is not something that you can control. And now going back to maybe your first question, how do you control? How do you actually implement resetting? Exactly. So imagine that you're running your computer code, okay, and you're trying to solve this problem, and you're running it, and you see that it's taking a long time. So what do? Sometimes you just give up. You kill the run, right? You kill the run, and you start fresh. And if this algorithm is stochastic, there is a chance that you're going to get now in the next trial a run that is completed in a faster time. So this is exactly the type of algorithm that you can implement in computer systems. For example, if you're running something and it doesn't complete up until some time threshold, just kill the program and start fresh. And we've recently published a paper where we actually showed that this method is highly effective in expediting molecular dynamics simulations. This was done in collaboration with the group of Barak Hirschberg. Now, there are other cases where actually biology was pretty smart, and it implemented resetting into the service process, even without us as human beings having to intervene. So, for example, in this case, the case of enzymatic catalysis, you have the binding and unbinding of the substrate to the enzyme, but unbinding actually acts as a resetting of the catalytic process. So you have resetting built into the catalytic process of enzymatic systems just by virtue of how nature designed it. Okay.
Sorry, my question is, how do you reset a bank queue, or let's say a bus waiting queue, ticket? You're waiting for a ticket in a queue.
Yeah. Okay. So going back maybe to the example of the supermarket, you say, how can I apply this to this example? And in this example, you're absolutely right. It's not going to work. Why is it not going to work? Because fluctuations in service time are not coming from the server itself. Rather, they're coming together with the job. Basically, you have people picking up different numbers of groceries before they come to the cashier, and now this number is quenched. So if you start serving and then decided you stop and start all over again, you're going to get the same number of groceries again, and so you're not gaining anything by doing that. So this is a situation where resetting is not going to work. But we focused in this paper on situations where fluctuations are intrinsic to the server. Now you can ask, what happens in maybe the gray area between the two extremes? So you could have situations where fluctuations are intrinsic to the server and solely to the server. You can have situations like in the supermarket where fluctuations are coming with the jobs. Basically, they're determined by the jobs and then they're quenched. Once you get to the server, they're completely quenched. And you can have situations where you have an interplay of the two, a little bit of contribution from the server, and then also a little bit of contribution from the job, and they come together to determine the complete service time. So this is actually a paper that we're finishing right now, the analysis and the writing of, and you can show that there is a threshold in between where resetting is going to stop working if you're closer to this type of scenario. But if you're closer to the type of scenario where you're controlled by service time fluctuation, resetting will work. But then, you know, exactly when and how to do it, these are the details that we discuss in the paper. So there's a lot of gray area between the black and white extremes of the supermarket and the example that I discussed today. And this is of interest because we want to come closer to reality.
If there is time, can I add 2 quick comments? Okay, sure. So you are going to reset now. Okay.
But there was another question. If not, you could certainly have the mic back. But I thought there was no question. So, do you want to stop questions after the next question?
Thanks. It was a lovely talk on an unfamiliar topic. So the number n is pretty small in one of the graphs which you'd shown. So the question, I don't know if I really understand this, but is there the issue of stabilization to like the time to stabilize to a steady state distribution relevant? Meaning the stabilization time to a distribution. For instance, here the n's are pretty small.
Yes.
I don't know if that is that a relevant question to ask there? Or?
So let me see if I understand the question first. So the numbers here are, you know, just a result of the parameters that we picked in the example. We could have taken an arrival rate that is closer to the service rate, and then you could have gotten here maybe numbers that are order of magnitude higher, 1, 2, 3 orders of magnitude higher, depending on how you take the parameters.
The question was that it seems to work even for such small numbers. When that's the point, that it seems to work for even numbers like 20.
Yes, so it works for even small numbers, but of course, and this is an important observation and point, if the difference is between a single person in the queue and half a person on average, then maybe it's not really worth it, right? But if you're improving from, I don't know, 100 to 2 or 5, then you're gaining much more. So this effect, I'll maybe show the PK formula again. You see, this term right here, it's large when fluctuations are large, but it's also large when rho is close to 1. So when the arrival rate is close to the service rate, when the server is already having a hard time coping with the jobs that are coming in, this term is going to be large because it's multiplied by a large prefactor. And so in these situations, exactly when numbers are high, when there are very long queues, then you would even be more inclined to deal with this problem of service time fluctuations. So it's a good observation, and thank you for it.
Thanks.
Shlomi, thank you very much for the talk. I think people here are eager to get lunch, even though there are more questions asked some
Yes.
myself. But
So go queue for lunch.
indeed. Well, we'll try
Okay.
your scheduling. I hope we won't stochastically throw anyone out of the queue. Thanks again for the talk, and let's thank all the speakers from the session again.
Thank you very much. Thank you very much. Bye-bye.